They,
Okay, sounds good.
Tony, you want to say like 5 words of introduction or something?
All right, this is Dr. Coykendall. He's been kind enough to join us from Clemson University, and he's going to talk on infinite sets and counting.
Well, thank you. Thank you folks for having me. I have actually visited Morningside a number of times. I have a couple of former students, actually former PhD students, and Mitch was actually an undergraduate when I was at MSU. I haven't been there in a while. I hope to be back. It is a much shorter drive to Fargo than it is from here. But hopefully when all this craziness is over, we'll be able to visit again. Anyway, as promised, I am going to talk a little bit about sets, in particular infinite sets, because they're the most interesting, and counting. So how many of you all have sort of a working knowledge of what a set is? Right, you've got kind of an intuitive feel. So
The 2 in real analysis don't raise their hands. They're kicked out.
So I'm gonna use naive set theory. So what is a set? A set is just a collection of things, or whatever things that you want. And the one rule that we're going to go by is if I have anything, I can tell whether or not it's in the set. So, for example, I could have the set of all people sitting in that classroom right now at Morningside College. Am I in the set? No, I'm not. I am a person, but I'm not in the room that you're in, for example. So a set is a collection of all objects. Naively, we're going to say, well, we know if I give you anything, I can determine whether it's in the set or not. So for example, you might look at the set of all the chairs in the room, all the desks in the room. You know, this is kind of a familiar thing. Now, let me ask you all a question, and this is kind of a warm-up question. Sets contain things, like I said, set of people in the room, set of chairs in the room, set of molecules in the room. You can just go bananas. But can a set contain itself as an element? What do y'all think? I mean, from a naive point of view, this seems like it might be a possible thing. Can anybody give an example of, from a naive point of view, a set that might contain itself as another element of the set? Any ideas? Well, I've got one. So this one's almost kind of smart alecky a little bit. You might consider the set of all abstract thoughts. That in itself is an abstract thought, right? So from that point of view, you might think of the set of abstract thoughts as an abstract thought instead of all abstract thoughts. Here's another example. What if I could somehow collect every set that is conceivable that has at least 2 things in it? All right, so here's one of them, the set 1, 2. I think we could agree that that's a set with at least 2 things in it. And how about the set A, B, C? That's a set with at least 2 things in it. Now, if I were to collect every set with 2 things in it, call it S equal the set of all sets with at least 2 elements. If this is a set, then it has to contain itself, because 2 elements of S are this and this. Everybody agree? This is a set with at least 2 elements, and so is this. So the set S itself is a set with at least 2 elements. So that's kind of weird, isn't it? Because these last 2 examples are sets that may contain themselves as elements. Seems plausible here, but we're going to see that this actually leads to some problems. And I'm going to call a set I'm gonna call a set for now, I'm gonna say a set is ordinary if it doesn't contain itself as an element. And I think that most sets that you encounter in mathematics or in your walks of life will be what you might call ordinary sets. The set of all markers that I have in this cup, that is a set of markers, but the set of markers itself is not another marker, right? The set of people in the room is not another person in the room. So I'm going to call such a set that behaves sort of nicely. I'm going to call that an ordinary set. Now, I see, I count 5 people sitting in that room. Am I correct?
Yes.
That's right. It's me.
As far as I'm aware, everyone here is a person.
Right.
Is anyone a cat?
I
No.
see Mitch. Mitch is probably a good church-going boy because he's sitting on the front row. I'm going to call that row that Mitch is sitting on, the front row. Now, quick question. Somebody answer quickly, speak up. Which is larger? The set of people who are on the first row or the set of people in the room that are not on the first row?
Not.
Okay, you answered that pretty quickly. Good. Let me ask you another question. See if you guys can speak forward. Okay. Here's 2 sets. I'm going to call the first set black dots, and I'm going to call the second one red dots. Okay. Quick, which has more elements?
Red dots.
Everybody seems to be in perfect agreement with that. Anybody disagree with the red dots have more elements?
Nope.
Okay, let me ask you a question. How many red dots were there?
More than black.
How many black dots were there?
7, 8.
Are there?
6. There were 6. 7.
I think it's 7. But nobody seems to know how many red dots there were. How do you know that the red dots are bigger? Right? I mean, I know how I compare. I know how I like to compare finite set. I like to check my bank account, see how much money I've got. It gives me a number that tells me how many dollars I've got. Right? If I've got like a collection of DVDs at home, I'm very proud of that. I know how many DVDs I've got. Right? I could count the number of chairs in the room. I could easily count that there's only one person, Mitch, in the first row, and there's 4 of you sitting not in the first row. How did you know that there were more red dots than black dots?
If you started erasing the dots one at a time, you're out of black dots and red dots left to erase.
I haven't counted the red dots either, right? But we can all put our eyeballs on this and tell if there's more red dots than black dots. Correct. Now, if I were to count, there would be 7 black dots here, and 1, 2, 3, 4, 5, 6, 7. There's 7 red dots here, and then more left over. Agree? And that right there is an important principle of counting, even though it seems a little strange. When I can easily count something, I know that if one person has 4 things and another person has 6 things, the person that has 6 things has more things than the person with 4 things. That's very convenient if the number of things is small. But how do you compare when it's bigger? And this is sort of what we did, I think, in our heads, is we sort of think, well, I see this collection of black dots here, and I see that the red dots more than pair off. If I sort of pair them off, I think I heard somebody say that, actually. If I sort of pair these off, there's going to be stuff left over. And this is an important principle in counting, especially when we get to infinite sets. Now, let me just introduce some notation, and then I'm going to give you an example. So here are some, I don't know if you've all seen this notation before, but the natural numbers, I call this the counting numbers, starting at 1, all integers 1 and greater. The integers is all the integers. So it's these plus the negatives and 0. The rational numbers. I can't really, well, I can't in an easy way write this down in the same way I did before. Rational numbers are fractions. Where both the numerator and the denominator are integers, and the denominator is not 0. And then the real numbers. You all see this in calculus, right? It's the real language used. How many of y'all have seen this notation before? Yep. This is familiar to you? Okay. Can we all agree that these are all infinite sets? Right. These all have infinitely many things in it, not finite. Well, if I wanted to compare them, which would you all say is the smallest, and which would you say is the biggest? How would you, if you were to sort of have a contest and see who's the biggest and then all the way down to who's the smallest, what would you say? Or does it make any difference?
The natural numbers are the smallest, and then numbers the biggest.
Okay, so you'd say this is the smallest?
Yeah.
Yep.
And this is the largest?
Yes.
I think I'd have to agree with that. That's what it looks like anyway. What about these two animals in the middle?
The integers as the second smallest.
Right, so from smallest, so size-wise, 1, 4, 3, and I by elimination, I assume that you mean this is number 2. Is that correct? Everybody agree with that ranking? Biggest, second biggest, third. Actually, you're sort of right. These are all number 2. These are all the same size. They have the same number of bubbles. Infinity is the same stuff. And this one is, honest to goodness, infinity is bigger than this. Huh. Now, what in the world am I talking about? Where does this come from? I mean, these are infinite things, right? How do I count them? And what do I mean by this is an infinite and this is sort of a bigger infinity? How do I do this? And this brings up an important idea behind how you count the infinite. Let me give you kind of a fun example before I go back to this and talk about why these are of different size or the same size. How many of you have ever heard of the Hilbert Hotel? This is one of my favorites. So you have what's called Hilbert's Hotel. Hilbert has infinitely many rooms. And his rooms are numbered like the positive integers. He's got room number 1, he's got room number 2, room number 3, forever. So he's got a very long hall and infinitely many rooms. Now, Hilbert is very lucky because his rooms are all filled up one night. He's got a full no vacancy sign on his hotel because all his rooms have an occupant. Well, late at night, somebody very important comes in that Hilbert doesn't want to turn away, right? Somebody, Kardashian or somebody that you want to have in your hotel. And Hilbert's got a full hotel, but he wants to put up this famous guest. What can he do? Does he have to turn the guest away? Well, the answer is Hilbert can accommodate this one more guest by doing this. What he does is he has his bellhop tell the person in number one to move to room 2. Person in room 2 moves to room 3. Person in room 3 moves to room 4, and the process continues. Now, guess what? Everybody has a room to move to because there's infinitely many. Don't try this with a hotel with 200 rooms. It's not going to work for you because whoever's in room 200, it's the shack. But we have infinitely many rooms, and so everybody can move down. This frees up room number 1, and all of a sudden, you've got accommodations for one more guest, even though the original sign said no vacancy. Can somebody, by the way, describe a process? What if instead of one guest that came late, what if you had 20? What could you do? What if you had 20 guests? What's that? Well, instead of having the guests from room 1 move to room 2, where could they move?
21.
Yeah,
Move
21.
22, 23, and so forth, leaving the first 20 rooms open for your new guests. Can somebody describe another process where you could have infinitely many rooms? What if infinitely many guests showed up? How could you accommodate that? That one's a little bit different because you can't just shift down the way we did. What if infinitely many guests showed up? You could have every guest in room number N move to room number 2N. Right? And what that would mean is after you made all the guests move, that every even number room would be occupied and every odd number room would be unoccupied. Now you've got room for infinitely more. Or you could go crazy and have room to move in square. There's lots of ways that you can make room in this Hilbert's Hotel for infinitely many guests over and over again. This is something that you cannot do in a hotel with a finite number of rooms. Otherwise, it would be great to be in the hotel business, right? But with the Hilbert Hotel, you can do this. Let me give you a similar problem. I'm going to bring it back to. This problem here. This is kind of a teaser for my abstract. Number. Okay, so here's the game I want to play. I have ping pong balls. I have one ping pong ball for every positive number. I've got one with 1 painted on it. I've got a ping pong ball with a 2 painted on it, and so forth and so on. I've got ping pong balls, 1, 2, 3, 4, forever and ever. And I have a giant bag that will fit as many balls in it as I like. I am going to play the following game. At 1 minute before midnight, I am going to put step 1. I am going to insert balls 1 through 10, then remove number 1. At a half a minute before midnight, I'm going to put in balls number 11 through 20, then remove number 2. At a third of a minute to midnight, I'm going to put in balls number 21 through 30, then immediately remove number 3. And at a quarter minute to midnight, 31 through 40, and move forward and so forth. I continue this process. And just for the sake of this problem, we will assume that I'm superhuman and can do this. I get it. I've got less and less time each time, right? It's going faster and faster. But we'll assume that I can do this, right? So, right. So does everybody understand what I'm doing? 1 minute midnight, first 10 balls, remove number 1. Second 10 balls, remove number 2, and so forth, so on. Question. At the stroke of midnight, how many balls are in that bag? Anybody want to take a flyer on this? Take a guess? Did I hear somebody say none? That seems kind of crazy, doesn't it? Right? Because effectively, what am I doing at each one of these intervals? Right? I put in 10 balls and I take 1 out. Then I put in another 10 balls and I take 1 out, right? So aren't I putting in 9 balls every time at every interval? Do I agree with that? Anybody want to take a guess how many are left? Zero. There are no balls. You want me to prove it? You guys are dying to see a proof, right? Here's my proof. Suppose there is a ball in the bag at midnight. Reach in, pull it out, and look at the number on it. What can that number be? Can't be 1 because I removed that at the first step. Can't be 2, I removed that at the second step. Can't be 3, remove that at the third step. If I give it any number in, I remove it at the end step. There are no balls left because what number can be on it? I pull them all out. Now, let me ask you a question. What if I change the game? What if I did the exact same thing? 1 minute to midnight, I put in balls 1 through 10, and then I remove ball 10. And at half a minute to midnight, I put in 11 through 20 and remove 20. A third of a minute, 21 through 30, remove 30, and so forth. Now, how many balls are in the bag at midnight? Now there are infinitely many. Can anybody tell me why that's the case? Let me ask you this. Can somebody identify a pattern for what balls that I pulled out? What do every ball that I pull out of that bag at some point in this problem, they all have something in common. Can somebody tell me what it is?
Factor of 10
And in 0.
or a multiple of 10, I guess.
Every number has to end in 0. Everybody agree with that?
Yeah.
How many positive integers do not end in 0?
Infinitely many.
Infinitely many. Now, this ought to make you mad a little bit, because when it was just 1, 2, 3, blah, 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 there are no balls left. When it's 10, 20, 30, there are infinitely many balls left. And so that should make you mad, because what that means is it matters what the number on the ball is. It matters the number that's painted on there. And in fact, I can change this problem and make this be any number. I can make it be 0. Well, I can't make it be negative, but I can make this be 0, or I can make it be 89, or like here, I can make it be infinitely many. Let me also point out another interesting corollary to this is that if I don't have numbers painted on the ball, you don't know the answer to this question, right? Because the numbers matter. And so if I have ping pong balls, there's nothing painted on them, the answer is not defined. Okay, so in counting the infinite, here a little bit. I am going to give you a finite example to show you how to count the infinite here. So this set and this set on the same side. Everybody agree with that? And now, yes, I know that there's 4 things here and there's 4 things here, and that's the easy way to do this, but let me illustrate something that's more overreaching. There is a function f from here to here. There is a function from here to here that is 1-to-1 and onto. What does that mean? That means the 1-to-1 part means no 2 things over here can go to the same thing. And onto means every star over here is covered by a dot, right? Another way to put this is everybody is paired up, right? Every dot gets a unique star under this function, right? This is the way that we count the infinite, right? We say, that 2 sets S and T are of the same cardinality. That just means the same size, even for infinite sets. Sometimes we'll write it this way. If there exists f from S to T such that f is 1-to-1 and onto. And by the way, if you remember maybe from calculus, this kind of idea you had there about reversing functions, inverse functions. If there's a 1-to-1 and onto function here, there's one back here. So if the cardinality of S equals cardinality of T, the cardinality of T equals cardinality of S. This is actually an equivalence relation. You haven't heard of that, it doesn't matter. But basically what it means is it functions just like equals does. Let me be a little bit more specific. If there exists f from S T such that f is 1-to-1, then cardinality of S is less than or equal to cardinality of T. And if there exists f from T, S to T such that f is onto, then cardinality of S is greater than or equal to cardinality of T. And if it's 1-to-1 and onto, you get equality. And also, and this is actually, you're going to think I'm a little silly for writing this down. And I am a little silly, but not for writing this down, because this is actually a deep theorem. But it turns out that and we won't prove this, but if that is, if there's a one-to-one function that goes from here to here, even if this is an infinite set, and there's a one-to-one function that goes from T to S as well, maybe a different function, then the size of the set is. So it turns out there's a one-to-one and a different, perhaps one-to-one and onto function. So this is the way we count. We can use this to count the finite. It's the same as just counting numbers. This thing has 4, this thing has 4. That's equivalent to say there's a one-to-one and onto function from here to here. But you can't really say infinity equals infinity, so this actually works in a more general setting. Let me prove the trouble. It's here. Consider I can think, see if y'all can help me think of a function from the natural numbers of Z that's one-to-one and onto. I'm going to do my functional assignment this way, and this is kind of a little wrapping thing here. I bet I can probably get a rule from this when I'm all done. Let's go 1, 2, 3, 4, 5, 6, 7, 8. You'll see what I'm doing here. I'm going to assign, this function is going to assign 1 to 0, 2 to 1, 3 to -1, 4 to 2, 5 to -2, 6 to 3, 7, and so forth, sort of wrapping its way out. I bet I can find a rule for this. He might actually tell what the rule is. Well, looks like to the evens, you cut it in half, right? N over 2, if N is even. I agree with it. So 2 goes to 1, 4 goes to 2. So I'm basically taking care of this bit. What if it's odd?
1 minus n over 2.
Something like that. See, I guess what I would do is take n, take away 1, divide it by 2, and then maybe take the negative sign of it, I think. So for example, 1 would go to 0, 3 would go to -1, and so forth. It's actually fairly easy to show. I mean, you can almost see it from my picture here, but it's easy to show that this function covers everything. So it's onto every integer is covered, and it's 1-to-1. Let me show you another theorem here that will help us count, and I'll sort of pull my answer up here. Let me remind you here that when I say n cross n, I mean all ordered pairs, A, B, where A and B are natural numbers, right? So n is just natural numbers in the raw, so to speak. This is any possible ordered pair of of natural numbers. 2, 3 is in there, 1, 7. 8, 6, 7, 5, 3, 0, 9, 201, all kinds of great stuff. It seems like this would be much bigger, but they're actually the same size. This one's a little harder to see. I'll give you actually two functions that work with this. One way that you can show that this pairs off the natural numbers and the order of pairs of natural numbers pair off is this way. Let's write down ordered pairs of natural numbers. 1, 1, 1, 2, 1, 3, 1, 4, forever. 2, 1, 2, 2, 2, 3, 2, 4, forever. 3, 1, 3, 2, 3, 3, 3, 4, forever. All of this garbage. Well, now I'm going to do kind of a trick like we did over here with this kind of looping bit. Well, one way that I can give you a 1, 1 and object function is assign 1 here, 2 here, 3 here, 4 here, 5 here, 6, 7, 8, 9, 10. So basically, I'm doing a snake. Like that. And as you can see, I will wrap through every possible order. I'll give you another function that's actually concrete. I can actually write it down. Also, we can define a function. F n m is 2 to the n minus 1. So whatever this is, it turns it into an odd times 2 to the m. I guess it should be 2 to the n minus 1. Otherwise, it would always be even. And I will leave that. This is actually a fun exercise. I won't spoil the surprise for you, but when you have an input of an ordered pair, this barfs out an odd number times power of 2. And that power of 2 could even be 0 if n is 1. Right? So it gives you a natural number. And actually see if you can verify that this function is 1 to 1. And you will use the fundamental theorem of arithmetic. That is, every positive integer bigger than 1 factors uniquely into primes. And the fact that it's onto is actually a little bit simpler. So, okay. Any questions? So actually, this shows, since you have actually pairs of natural numbers are the same thing as the natural numbers, and since we have the natural numbers are the same size as the integers, here's what we have so far, which is kind of interesting. And it's a little bit counterintuitive until you get used to it. But what we have so far is the size of the natural numbers, that infinity, is equal to the size of the integers. And you can use this previous theorem to show that this is also the size of the rational numbers. And this is fast and loose, but the idea is rational numbers you can think of as ordered pairs because you have a fraction a over b. So you can think of that as natural number, natural number. Now you have to muck around a little bit with the sign, but that's fairly easy to get around. Okay, so even though it's counterintuitive, we now know that the size of these three infinite sets, they're all the same. I'm going to give you a famous argument here. This is a famous infinite set argument. Let me explain to you what I'm claiming. The natural numbers is an infinite set, 1, 2, 3, forever and ever, and it's the same size as all these animals. But it is genuinely smaller. It is a smaller infinity than the number of real numbers that are even between 0 and 1. So if you try to list all the numbers between 0 and 1, you will find, in fact, not even including 0 and 1, but you will find that the natural numbers are, in fact, bigger. Okay, so let me actually. I want to make that a closed interval, just because it makes my life, what I had written before was true, but this is much easier to show. Okay, so certainly the size of the natural numbers is less than or equal to the size of 0, 1. Let me give you, remember what this means is there's a one-to-one map here. But f of n equal 1 over n. So take 1 to 1, take 2 to 1/2, 3 to 1/3, 4 to 1/4, etc., etc. This is a one-to-one map. So the size of this is less than or equal to. How do I know? The interesting part is this infinity here is actually smaller. And the way that I'm going to show that is I'm going to try to get a contradiction. Let's suppose, and this is actually an amazing mathematical argument that did not really surface in the mathematical community until like the turn of the 20th century, really. Suppose that so there exists a one-to-one and onto function f from the natural numbers to 0, 1. Okay. And I'm gonna make a chart of what f does. So here are my natural numbers: 1, 2, 3, 4, n, and this goes on forever. Now, each one of these should correspond to some number in the interval between 0 and 1. And so I can write this as point A, so it's A11, A12, A13, A14, etc. This will be point A21, A22, A23, A24, etc. A31, A32. Now, I'm going to have to be a little bit careful here. So let me give you kind of a caveat. By the way, does anybody see a possible danger I might run into? By the way. Well, one danger that I might run into is follows. Sometimes there are multiple ways of writing decimals. Are you guys familiar with this? Like, for example, 0.09999 forever will be is the same thing as 0.10000 forever. Right? And so what I'm going to do is I'm just going to stick with one representation. So that is to say, I'm going to, instead of ending in all zeros, if I've got an option, I'll end in all 9. So I'll never write 0.10000. I will prefer to write 0.099999. And the only option that where I can't do that is I have 0, and then I'm forced to end cross the rows. Okay. Now, if these are the same size, I should be able to pair off every natural number with every decimal between 0 and 1. Agreed? So everything's covered. Every possible decimal expansion between 0 and 1 should be covered in this right column. But that can't happen. And I'm going to show you why. I'm going to now build a new decimal. Where I am going to define, I'm going to let BI be 6 if AII is not equal to 6. And I'm going to make it be 5 if AII equals 6. My choices of 6 and 5 are arbitrary. I did want to avoid 0 and 9, so I didn't have to re-explain things. So what this means is, this is the way I define BI. I'll look at A11. Is that 6? If it's not, I'm going to let the first decimal be a 6. And if it is a 6, I'm going to let the first decimal be a 5. Right? So I don't know much, but would everybody agree that my BI is a string of 6s and 5s, right? But notice that, more importantly, this decimal, B1, B2, B3, etc., cannot be in red right column. Anybody tell me why? What my claim is this new thing that I built, which certainly, since this is a string of 5s and 6s, is somewhere between 0 and 1. This is a decimal in the interval from 0 to 1. It cannot possibly be over here. Can I explain why? Well, if this thing is here, it's got to be one of them, right? Can this thing be the first one? Can it be this first one? Well, no. And the reason is the first decimals don't match. Because look at the way I define this. If A11 is equal to 6, then B1 is 5, so they don't match. And if it's not equal to 6, then I make the first decimal 6. So in any case, the first decimal doesn't match. So it can't be this one. Okay, maybe it's the second. But look at the way B2 is defined. B2 is 6 if this is not 6, and 5 if this is 6. So this is not B2. So this one doesn't match in the second decimal place. And this one doesn't match in the third. This one doesn't match in the fourth. And this one doesn't match in the nth place. That means this is new. It's not in this list, which means that this function can't be onto. There has to be stuff left over. This is a huge theorem because it says that this infinite set is true, honest to goodness, smaller than this one. And I'm not going to keep you all too late here, but let me give you a theorem that I'm going to give you two theorems that I'm not going to prove. But if you're dying for me to prove, I can prove afterwards or send you an email or something like this. But here's the first, and this has an interesting consequence. Here. Well, let me give you a quick definition first. If S is any set, then PS, this is called power set, is the set of all subsets of S. So let me give you a couple of theorems. And the first one has to do with power set. And the proof of this has shades of this theorem we just did. If S is any set, then its power set is genuinely bigger. This is even true if the set is infinite. A consequence of that is there are infinitely many sizes of infinite sets. Start with an infinite set. Look at this power set. It's a set of all subsets. That's a bigger infinity. Now you got a bigger set. Look at the set of all its subsets. That's a bigger infinity, and you can go forever. And here is the last theorem. There is no set of all sets. The proof of this is actually surprisingly elementary, but it came along, Bertrand Russell realized this in the early 1900s, and it set theory on this. This was a fundamental crack in set theory for when it was discovered, actually in the early 20th century. It has since been fixed, but it's surprisingly elementary. So I know it's late. I won't keep you any further, but I certainly would entertain any questions. I think I lost your sound. Oh, there we go.
Man, that was
Okay.
applause too.
We had a round of applause, and now we'll see if anybody's got questions.
Any questions, y'all?
I suppose I got a question about the ping pong ball game.
So same, I do too.
So I've actually had a question on that for a while. How do you get to midnight? Right, if we're assuming that you take one out at it, so you end up getting to midnight.
It's a limit. It's like Zeno's paradox, right? Are you familiar with this? Or the old thing about Achilles and the tortoise, right? So I bet you think you can run faster than me, which you certainly can, right? I can't even see you really, but I can guarantee you can. So let's suppose that I'm, which maybe let's suppose you and I are going to run a 100-yard dash, and I'm such a big fat cheater that I take off and I'm 40 yards ahead of you before you start off. Now let's suppose that you're as fast as Usain Bolt, right? And you're going to beat me, right? Well, I've got a 40-yard head start on you. And so when you put in the guns to catch up to me, maybe you're running faster than me, but I don't care how fast you run, in the time it takes you to get to my position, I've moved, correct? Now, I'm not 40 yards ahead of you anymore, but I'm a little bit ahead of you. And you have to cover that distance to catch up to you. And in the time it takes you to cover that distance, I'm ahead of you again. And so forth and so forth. So from that point of view, you're never going to catch me, no matter how fast or slow I am. But we both know from experience, right? I mean, you've seen runners pass one another in a race. There must be something wrong with that. But of course, part of the problem is you have a convergent process there. Because yes, you have to catch up to me every time, but the time it takes you to catch up is shorter and shorter. Right? Now, what I described with the ping pong balls is physically impossible to do because the time intervals get too small, and we can start talking about quantum mechanics and what kind of length time is on, et cetera, et cetera. But what I'm talking about there is how do you get to midnight? It's a limiting process. right? Because every one of those intervals is going through a shorter period of time. So in a finite time, you get, right? We're putting the intervals on smaller and smaller lengths. It's a little bit hard to wrap your head around. Does that make a little bit of sense?
Yeah. Thank you.
You heard that before.
Yes, thank
Other questions?
So this is probably a dumb question, but say you have a set with infinitely many elements.
Right.
We'll just say, like all natural numbers. If you double every number in the set, does the set actually get any bigger if you double the value, but not the actual number? I guess now that I'm saying it out loud, it's probably a dumb question, but I don't know. I was just thinking.
So actually, I mean, I can describe, well, actually, you should correct me if I start to describe something, is not what you meant, but so suppose you have a set of natural numbers, the process you described, so you start off with a set of natural numbers n, and you've got 1, 2, 3, and 3, and so forth. And you describe a process where you double each. And what you will have here is what is sometimes called 2n. So you'll get 2, 4, 86, like that. And actually the sets will be of the same size because the function that you have here takes n to 2n, right? And your input is a set of natural numbers and your output is the set of twice the natural numbers, which is sometimes called 2. And so, yeah, these two sets will be of exactly the same size. You can compare them.
All right.
Others?
I have one about the ping pong one as well. So the one where you, like on step 1, you took out number 1, and step 2, you took out number 2. You said that there's going to be no balls left.
Right.
So then I tried to like find a way to say there would be 1 ball left. So you said you like stopped, if you stopped at n, would there be any balls left? But on every single step, right before you took out ball n, you added ball 10n. Could you say that ball 10n will always be in there?
Yeah,
So
but
like
you're
10,
going to reach 10n later in the process and take that out, I
right, but on that, so on step n, you take out ball n, but you don't take out ball 10n. So ball 10n will always be in, I think. I was just trying to think of one to keep one in there.
Oh, so the process, what you're trying to do is figure out how to leave a ball in, like one ball.
Yeah.
Okay. Well, I mean, you're going to get a little mad at me for this, but there's many ways to do it, and you can do exotic things where you flip it around and just one. Well, one thing that you could do is one thing that you want to do when you do this is you can put in balls 1 through 10 and remove 2. And then put in balls 11 through 20 and remove 3. And so forth. And ball 1 will be left over.
Okay.
And you can play this game by starting at like 250, right? Or yeah, right. You can start at 250 and that'll leave 249 balls. And there are other things that you can do that are more exotic where you can leave strange patterns and so forth. Because actually, basically it boils down to there's infinitely many functions from the naturals to the naturals, and you can do all kinds of wacky stuff with it.
All right, let's thank.
Oh no, thank you all for having me. I'm a big fan of Morningside, so I hope to come visit y'all in the future soon.
Well, we would be happy to have you.
We'd rather come where you are. Quite
We're coming out of winter, it's not so bad.
Are you,
Right.
are you all in session now?
Yeah, we had spring break last week, and so we're back this week. We've got a 5-day weekend around Easter, and